Hi everyone, this is Prakash here. We are on the quantum computer fundamental session 4 and we are going to deal with Pauli matrix. Before we jump to that, I just want to make sure part 1 is what I cover, part 2 will cover, and this is we have 4 sessions, June, July, August, September. We have finished 3. This is the 4th one, part 1 session, part 1 of that, and part 2 will focus on it. This is more to do with the quantum fundamentals, quantum circuits, quantum algorithms, and quantum uh, complete algorithms as we go to the 4th session. I just want to recap from last 3.7. We had some items we had moved to the session 3, and that is eigenvectors, eigenvalues, finding the factors, as well as some remarks on the eigenvectors with significant that's in the group. After following that, we are going to go to let me begin with last time we were trying to represent blocks here, and then some intuition we wanted on the matrix representation. So blue, brown has 3 blue, 1 brown has a special eigenvectors and eigenvalues graphical representation in one of those visual pictures. Most welcome to see that. It shows the subspace from 3 to 2D to 1D. 1D is a line, 2D is a 3D volume or a cube or paralleloid. That's what the illustration is, and you can definitely look at how the stretching and squeezing happens in a given subspace. What is the rotation happening to one? And these are all vectors. Now let me go to the third session. Certain things we are trying to get to, and we are to the operator. So we have sigma x, sigma y, sigma z, and we have taken 2 of them, sigma z, sigma x. So sigma z is in matrix, and it is 1 0 0 minus 1 row followed by column. So row 0 column 0, row 0 column 0 column. So it's 1 0 0 minus 1 matrix, which is the of sigma z, or as we call it Pauli sigma z. And for now, remember the matrix, and this matrix to be multiplied with a column vector which is k0, k0, and column vector k1. So in operator, this is the operator, matrix operator, operating on a vector to produce another vector, and when it does that, it results in some scalar with plus minus 1. And to look at them, I show you this specific matrix in a separate, so that it's easy for you to understand. So 1 0 0 minus 1, so sigma z, this is a 2 by 2 matrix, and this 2 by 2 matrix you want to multiply with a k0. K0 is enough. Let's say column matrix 1 0 is represented by that, is represented by column 0, and k1 is represented by column 1, and both these are nothing but sigma z. We are just multiplying with 2 vectors because these are the 2 vectors spin up and down. So when sigma z matrix is multiplied by the spin up k0, you do the row and then column. So that is the matrix multiplication. So 1 into 1 plus 0 into 0. Then there is 0 into 1 plus minus 1 into 0. So if you sum this, is 1 plus 0, 0 is equal to 1. So ultimately, the vector H0 is 1, 0 column matrix multiplied by Pauli matrix, you can call it sigma z. You get back the same. So it preserves it. You just call it as plus 1. Same way, when you multiply 1, 0, 0 minus some same Pauli matrix sigma z with H1, which is 0, 1, it's spin down, and the multiplication goes again similarly with 0 by this column, 0 by this column. So this first one, that is column 0, sorry, row 0, with the column of this, which is 1, 0, 1, 0, plus 0, 1, and that happens to be 0. So 0 minus 1, 0 into 0, plus minus 1 into 1, which cancels with a minus 1. And so we have got a, of course, 0 minus 0. So we will put a minus out of it and we call it 0. So when you multiply the column 1 by this Pauli sigma z matrix, it results in a minus 0. So basically, we get a result of K0 and K1 as K minus 1. So this is the representation. So this is very important for us from fact that we are doing matrix multiplication and associating corresponding basis K0 and K1, which are the spin up, spin down in the quantum space. So that's what I wanted to represent. I will again make sure that quick from this and get back to our presentation. And I want to ensure that this presentation is easy to use. So I think I will share. Then that should be last. Let me do that to here, stop share and share. So from this and share it. Hope you have got back to the share. The share was not there. So this is what we were trying to do, and this is with respect to z-axis. Now, when we tried this z matrix on plus minus last time we had done, presumably presented to you, we saw that we had to translate the plus minus this is x axis. If we had to do with respect to that, then we ended up saying that the that the value of k plus turned out to be in terms of the k0 k1 which is z-axis basis, turned out to be 1 by root 2 plus minus 1 by root 2 plus k0 plus k1, which is the combination. So we have 1 by root 2 and 1 has the vector. And whereas for the minus turned out to be 1 by root 2 k0 minus k1, which is again linear combination of k0 k1 with a minus sign between 1 by root 2 and 1. So what we say, if you want to interpret, when we say z basis interpretation or sigma z interpretation, the magnetic device that measures is perpendicular or parallel to z-axis, so that the spin that occurs on the electron gets attracted either it spins down or spins up based on what energy it has. It has low energy, then obviously it will float up like in water and go down if it is heavier. So we say spin up is a lighter level, and just for the analysis I'm saying, but that's what it is. So when we operate on a basis which is different than K1, K0 vectors, and that will be different vectors, then matrix may be different, and not maybe will be different. And so we have some combinations of vectors which are possible, and I just want to make sure that when you operate, there is use the matrix as the operator and operate on the basis vectors, it results in an eigenvalue provided, of course, if it is unique. If it is not unique, if you don't get the measurable result, measurable in terms of plus minus 1, then that vector has no value for us as far as measurements are. So for measurement basis, we want that they should be resulting in some value which is plus minus 1. That's it. And we deal in quantum mechanics or quantum computation, all with plus minus 1. So we do have the Pauli matrices which I shared with you, an example of this on the screen. And we have seen that these 3 matrices, and you have to remember them. So assuming that you remember them, I will just move on to what happens to sigma. This is a change of space. The space was with respect to sigma and the z-axis. Now if the space is measured in terms of x-axis, then your magnetic device is going to be measured will be in the x-axis direction with the north south pole, so that the electrons accordingly go left or right, which is equivalent to enough sigma. But for that, the measurement basis will be sigma x. And so, what is the eigenvector if we want to find out? And if the eigenvector is 0, 1, 1, 0 of sigma x, then what is the vector eigenvector? Because we know the matrix, then you can find the vector. So we are taking E here. So when we multiply 0, 1, 1, 0, we are going to get 0 into E plus 1 into F, then 1 into E plus 0 into F, and so we are getting for a vector EF, it gets into equal to F. So what we can do, we can say that sigma is but a matrix which you can represent as some scalar gamma, and the eigenvector is this. So if gamma times the eigenvector of EF is equal to F, that means you have got E equal to F, gamma E equal to F, and gamma F equal to. So if you try to solve this, you will get, you can just multiply both of them, both equations, into F is equal to gamma square into F. So here we will get gamma square is equal to 1. So this is what it is. Gamma square is 1, then the eigenvector should be plus minus. So we can get a plus minus 1 for a 0, 0 as a eigenvector. You may get more than that, in the sense that it's not necessary that these are the only ones. So then what? So eigenvector and eigenvalue for sigma and a space vector. So assuming that we have got what we want, and it turns out the last time we have said that if you want a vector, it should be unique, and therefore we are able to get, but that vectors are not here. Now what we do is we try to solve that and say gamma equal to 1 equal to our modulus E square plus X square equal to 1, and then F is equal to, so coefficients F are 1 by root 2, E equal to F equal to 1 by root 2 for gamma equal to, and for gamma equal to minus 1, we are getting E square minus equal to 1 and E equal to minus X equal to 1 by root 2. So therefore the corresponding eigenvectors are 1 by root 2, 1, 1, and 1 by root 2, 1. For the case plus and case minus. Since here may be complex number, there are actually finite number of. It's not just that these are the only. But then what is the difference? The difference happens because of the phase factor. So what is the phase factor? So every solution is different. For plus minus factor, similarly for any other angle. So angle of the theta with respect to the axis will be different. For like for x axis it is different, for minus x axis. So for any other theta, then the phase factor will be different. In solution there are a number of, but those solutions may not be constituting the eigenvectors with eigenvalues per measure. So we get e raised to I theta cos theta. We can expand that. Now we are not going to detail. We are just summarizing that. The e raised to I theta of I is nothing. I square is minus I number, complex number. So e raised to I theta is put in the vector. If you multiply that, we can get a ket. V ket. Instead of V ket, if you multiply the V bra, then you have to take the complex function as we have seen previously. So what it means is that e raised to I theta ket, and then if you do a bra, then you have to do multiply that with e raised to ket minus I theta, because I a complex number is equal to minus I theta. So if you multiply the bra and the ket vector, you can get a theta I theta minus theta will cancel. You get a what you call, because they turn out to be e raised to I theta and e raised to minus theta will turn out to be unity. Therefore, this will become a dot product of vector v, which is bra with v, and so the phase factor will disappear. The only important thing to note is this phase factor is important from point of view of achieving interface. So if you want an interface to cancel, or if you want that to be enhanced, that is aid to get higher amplitude or something, then interference is minimized, and that's why we would say that the phase factor is important, and we'll come to that in later. We do the gate, some of the phase gates. So at this time, I will just conclude that we can have vector v and u, and if we do if the vector v and u are not similar, then it's not a complex multiplication of u, that means it is not scaling. The scalar is not the factor between v and u, and yet we still find some possible cases where eigenvectors have values, which are eigenvalues, and call them they are degenerated, and we discard the subelectrons which degenerate. So operators are represented by matrices using they determine the evolution of vector quantum state and vector. So basically, it rotates in the hyperspace based on the operation of the matrix, and there are special cases where they happen to be eigenvalues happen to be plus minus 1. Those corresponding vectors they are called as eigenvectors, and this is for observation. For observation, for using to make sure that basis by which measure are real in the two-level system like we do in the classical computing. Therefore, we prefer to have measurement based on the eigenvalue. So, whatever we have done right now, we still, because our classical computing is more advanced, we still have to do hybrid measurement. We are not currently totally quantum computing, all with quantum and quantum metrics. So 2-bit operations are there, but that is for speeding up the workload and whatever happen to be with the subatomic particle. So one subatomic particle creating one what do you call the spin, and multiple phases, you can form the resistor. and then you can like your classical computer do the operations like you do with right? So we multiply the add the qubit superposition theorem to that guy and use them. But at this time, it is important to know that eigenvalue is important for big eigenvalue so that we can compute them. And, it is useful for interpreting. So that is the portion of session 3. I'll give to session 4. We are talking about the electron spin. And remember the operator is not for measurement as a measurement, the random operator. If you do measurement with a magnetic device, the state will collapse to one of the basic states. And but before even doing that, you want to measure the operation of the operator and predict what can be there. And the prediction is obviously probability. It can be either of the locate 0 or taking state as it is B as it. But it is important to know that electron spin is one way of looking at binary digits are 2-level system or 3-level, 4-level very different, but 2-level system is very different. Therefore, because it can be 2 to the power of n, you have 2 given 2 to the power 2, and so binary is a 2-level system. For classical, you want to reutilize, but with a electron, physical electron element being different, quantum units are the standard specific stand or not just. So we will now look at electrons. There are some magic kinds, got it, magic, but they are called polymetric, and polymetric sigma x by b along with sigma 0 is identity. So let's get into the polymetric. So there are 3 matrices, sigma x, sigma x, sigma b, and what we know. So if we go to this one, you can see we had tagged 0, 1, 0, I minus 1, 0, 0, 1, 0. So sigma x and sigma y both are diagonal right to left. Whereas they have x as a 1 on the left, very top to left, b 1, then it has a y as a I. On the contrary, these two methods, sigma z and I and sigma 0, both have diagonal to the plane as 1, 1, and 1 minus 1. Sigma 0 is 1. Identity method is 1. So just one of them puts it to minus, it becomes sigma. So to remember the polymetric xy are these identity method. Remember that, then you just have to represent the diagonal what comes for x1, for I minus I for the sigma y, and for sigma z minus 1 is the part, and then the k 0, 1, 0, and k 0, 0. If you see something in the water, then it goes down. If it is so you can say that if it is up, then the light, the spin up is 0, 1, 0, and that is k 0. So k 0 is lower, 1, 0 spin up, and k 1 is 0, and 0. And so tendency towards low or high property. At a given time state, they are 0. So this is how to memorize polymetric, how to remember 0 placement, because these are the fundamentals for us going forward. And you remember that I square equal to minus I is imaginary. And so these are complex, scalar complex numbers. And all polymetrics are defined on the basis of 0, 1. So you will always have this one as a K0, K1, this is 1 0 0 1 for up and down, and sigma. Other thing if you need to remember is x square, y square, z square. Oh, sorry, sigma x square, sigma y square, sigma z square. These are always equal to 1, and if they are so they are equal to identity. So I think I will take this off and go back to that. This is the 2. Let's continue. So what we have is sigma x square. Property 1 is that sigma x square is sigma y square. Just wanted to make sure that I don't want to lose this use the card. Top share and free share. And free share. So here we went from polymetric sigma, and I need to metric of sigma 0. The property 1 of the polymetric is then call it metric. Whatever. It's sigma x into sigma x. So the sigma x take a 0, try multiplying into column 0 into 0 plus 1 into 1. This is 1, and similarly 1 into 0 and 0. So 1, sorry, 0 into 1 into 1 into 0 to 0. 1 into 0 and 0. So this is 1, 2 elements, and then we calculate the 2. And essentially what it means is the identity. So sigma x square in computational basis, you create a 1 from the identity. And sigma y also you get is part of the equation. And so there is 2 more important things. The property 1, if you have a identity and you multiply by vector, you are going to get the vector. So you are using column vector as one of the vectors, and if you do identity matrix 0 1 0 0 1 multiply it into that is vector. That means you are getting using as vector, and that is you are getting the vector. Same way I am, and then I have matrix, and you are multiplying by gives a result in identity matrix which you multiply by vector and multiply by matrix. So that's the one of the properties. Let's go to the poly from poly to the electronic. Of course, electronic I have described two level system, and you prefer a 2 level system and build on it 1 qubit and 1 qubit at a time to build the register memory as public. So at this time, I just want to mention as I have done I is equal to I is equal to this is computed. The commutation is not possible. Sigma x. That means they are anti-commutation. That means sigma x, sigma I into sigma j is not equal to sigma. If I is not equal. If I equal to j, you obviously sigma x equal to sigma x square equal to. If they are not equal, if I and j are not equal, then sigma x sigma j, what you say, you can try to subtract by multiplication of those two matrices. You will find that they are equal to if I not equal to. If I equal to j, you know it is equal to sorry, if they, because if it is 1, sigma j square 1, if it is j, and this is sigma j square 1, so 1 minus 1 is I equal to. But at the same time, you have to remember, you can also do a plus, not just minus. So if I do a plus, then what? So that's the difference. So that's why I would say the equation property of anti-commutation, and we are saying that the whole thing is that either you do XZ and prove that they are something different, they are not equal, and so these are not equal. X not equal. As I told you earlier, I was walking 10 feet straight and looking left is different from looking left and walking 10 feet and they are not equal. So that is the position. So therefore the product position of the matrix is different here, is different, they are not same, and therefore that means commutative property A into B equal to B into A is not true. Like in same way, so anti-commutative, that is why we say, but at the same time if I say A into B plus B into A, then the what is, so that turns out to be a twice of the identity. Then you can prove it, because if you have matrix here and V and A and V and X, and if they are same, then sigma X square is 1 I, and sigma J square is V replaced by X against X square. Okay. So if they are equal, then they will become 2. When you add them, you get 2 of I. So the Kronecker notation, but a pillar which is allowing you to describe the same equation. So if you have curly bracket sigma I, comma sigma J, mathematical representation of sum of AB plus BA, then that turns out to be either twice the identity matrix, or if they are not equal, then sigma J equals 0, so it turns out to be 1. So that's the representation, and that null matrix is what we have here, because if you take this XG, if you add this 0, 0, minus 1, minus 1, 1 minus 1, 0, 0. So it will turn out to be. So that's what from that we get. So what it means is that either you get a 0 or you get a 2i. And to represent that Kronecker delta notation, that delta xg equal to 0, x is not equal to, or if it is equal to 1, then it is 2, or 2 delta xg additive. So all three polymetric might be looked at are anti-commutative. That is, you cannot have one over the other, then the vector will be the same as you say. So as I mentioned, you are having vector v in standing position somewhere, and then you walk 10 theta 10, and then look right. So that's one way. The other way of turn right and keep walking 10 feet and look right. Those two are not good, and that is really non-commutative, anti-commutative, and that same thing is expressed by the property that sigma I is not equal to by not equal to j. This is just very similar to what we did in the orthonormal when we use the Kronecker delta function, but with respect to orthonormal. Now I will move on to spin operation in arbitrary direction. Now what happens is when we are trying to present sigma operator or a matrix, correspondingly we want to calculate it in direction. So n is there in a hyperspace. So we are not looking at right now the xyz, but we are looking at hyperspace. So sigma n equal to vector n into, now actually what is doing here is, why is there this? We are looking at arbitrary direction which is n. So I'll show you the diagram Pauli. Here is the n direction. So xyz, you are just mapping them according to n as a component of c, and I want to represent them as a combination So vector n with a nx y z comma. And we know that when we take a vector, we can normalize it. Normalize it means that we have to make sure that they are on. To make it easy, we say that okay, let's say x, y, z are the direction, and then let's just multiply x, y, z column vector with the row vector, and so y row vector because k can draw there and dot product. So if I have a column vector represented in cap arrange hat as an x and y, coefficients of this and normalize the vector by multiplication. So that um, row vector transpose of it is rotated anti-clockwise. So nx and y put in goes into matrix P1. So this is the norm. We have done this. Now with respect to normalization for n. Now what happens? So here spin operator sigma is in the direction n. So we can think of sigma being n direction rather than z. So and we are representing the vector n from the as component unit normalized one time. So if we say and like they are interchangeable in the sense that a matrix is interchangeable with a vector and vector is as long as value it's only the matter of time. So if we are that's the case, Pauli matrix we can represent as Pauli vector. So the notation is the reverse. All we are doing is we are doing the x, y, z and saying that Pauli vector in n direction is composed of this, and accordingly we can represent instead of the nx sigma as we took here, instead of we are taking the matrix. So you have got 0, 1, 0 polymetric for x, 0 minus I 0 polymetric for y, and 1, 0, 1 polymetric for z. So we are in fact changing the Pauli matrix to Pauli with a vector n as the vector, and these are the Pauli. So we can even represent, so they are interchangeable. In this case, we call this Pauli vector. Previously, we call it as Pauli. So then the question comes: if we call Pauli as a vector, Pauli vector matrix as a vector, what is n? Is n a matrix? Of course, n is a matrix, and so you can even represent that as a matrix, and we have got here ns and multiplication addition, ns multiplied by the vector. So we are treating now reverse, one being matrix, other being the scalar, but all are actually vectors. So is n a vector? Is n a matrix? Yeah, it is a matrix. You can see, even though we call it vector, we can compute the value. But if you want to really justify this, you can try out by zeroing, let's say x is 0 and here is 0, 0. That is you can put it 0 and is 0. If that happens, it is value is 0, 0 minus 5 and 0 I 1. Of course, I 1 I, and then this is minus. So this is equal to 0 minus I. But this is what we call it sigma n. So sigma n turns out to be sigma y. So basically, you can interpret. Can n be a matrix? Can sigma be a matrix? So polymetric, polyvector, whatever you want, interpret as needed when needed. And this is true, specifically very good for our n dimension. So spin direction, in 3D space, we say our ket 0, ket 1, arrow, up arrow, down arrow, left arrow, right arrow, and so on. And As a programmer, we can afford to ignore the directions and all that because we are only doing logical. So when we do logical work, it's okay, whatever we refer enough down on that. For us all, we look like we can let it just do the command, but that's not. We can afford to ignore them, but the analog circuit hardware who are doing energy level the subelectron, they have to distinguish between logical and physical. They have to distinguish between the isometric spaces and what is the space, whether it is with respect to basis, what basis. So what is the basis K0, K2, or is it with respect to plus minus basis, which is the x-axis, or is it minus I basis, which is y. So these are the only three bases we have seen, but we have also shown that any arbitrary direction can be taken, like n basis, n vector in any. So essentially, they need to know because computation, otherwise, what is represented. If you don't, if I like me speak Japanese and you speak German and English, if I don't tell you I'm okay, and then tell you you understand what I have said to you, to a Japanese, and they will say, what is this? I don't know what you're talking. This is not my language. So I don't, my basic is Japanese, your basic. Can you please translate? So whenever we generally conference with Japanese, we also have an interpreter in the interview. So same way we need to have plus minus interpreter if we are going to present x-axis as the basis. So our basis we have taken G basis or n basis. N basis means it is the vector space. You can map it to any. Essentially, this is what the essence that you need to know measure when you do measurement point P and point Q. Then between P and Q, whatever the distance long distance L is there, or whatever small distance L is there, that L distance is the vector. So the vector has to have origin, which is now proximal for cubic, and unitary unit sphere, which is the surface of a unit number unit measurement. So if I say 1 meter, then 1 meter all around. Is 1 centimeter, then 1 centimeter. So whatever our unitary normalized to, that is the one is used as the unit. So unit is important for measurement, and therefore we end up. And not only unit is important, you also need to know what is this. Are we measuring meters? Are we measuring centimeter? Meters what? So therefore, unit of measurement is important, unit is important, and that is why our vectors have to measure in terms of basis, and those bases we interpret them as eigenvalues and eigenvectors. Eigenvectors are the K0, K10 space. This is the standard in the industry, as in the physics and other computation materials. Mathematics, will come to that, but at this time, you can say basis is important. And they are also tensors are also the base of vectors. It is independent vector. The hyperspace we are talking about is independent. So the relationship between spin direction and relativity space we have established, and we are looking at now a little bit advanced the matrix operation. A matrix said to have an adjoint matrix, adjoint mirror image, right? So if you are looking at the mirror, you say right, and you see in the mirror, you say opposite of it. Like in photography, the negative, right? So you have to take a positive image of the data film. If you are old age, it's not today you get a flip of a button on your phone. Just to touch it and it will show the reverse camera. So same way, it's the image. So essentially what I want to do is a matrix, in this case II01, the image of that, if you take, is computed mathematically without just say complex conjugate of it and a transpose, and you will get example. I you take a complex conjugate of it. I so real numbers they stay as they are. Imaginary number like I becomes minus, so I goes to minus, I goes to 0. So this 2 by 2 matrix, you have taken a complex. If you take a transpose of it, then diagonal elements are 0, 0, 1, because A is C, A is J, I and J, they are same, so they will change. But this example in the 2, they get transposed. That means minus 1 comes here, so what we are saying, minus 1 from there to there, 0. Otherwise, minus 1. So this is the complex conjugate of the transpose of this matrix with A and this is this. Are they same? They are not same. So you will get adjacent matrix, but they may not be self-adjacent in the sense they are not equal. But if you find that you take a complex conjugate transpose of the matrix and it turns out to be same matrix, then you are that is the adjoint, self-adjoint matrix or Hermitian matrix. So if you have Hermitian matrix, they are self-adjoint and they can be represented as A dagger. A dagger is nothing but complex conjugate of transpose, and the elements of A, J, I dagger is equal to A, I, J star. Then, but if in specific case when they are Hermitian, then you want them that A, I, J dagger should be equal to A, and then A, J, I equal to A, J, I star. That means either way it is complementary. You take here or here, you take here or here. Either way, you go forward or you go backward. That means transpose of the conjugate of matrix is itself the matrix. Then you can play with it. Like it doesn't matter whether it's the cat space or brass space, which is what we want for quantum computation, and therefore that's what it means. So adjoint of a matrix is nothing but matrix, complex conjugate of it, transpose of it, and if you find that it turns out to be the same matrix, then you have achieved what you want, which is Hermitian matrix. And only Hermitian matrices have eigenvalues, they are measurable, and therefore all quantum phenomena. We would like to bring out any transformation to get it to plus one. So it's important. I will summarize it. I'm done with my presentation for the portion which I have responsibility. That is, we say that we distinguish scalar, vector, matrices, and things involve like K0, K1, plus minus, and plus I, K I, K minus I. Those are the three XYZ equivalents, and those are important for us from point of view of spaces are we call it isometric spaces, isometric spaces, and we also spoke in the beginning about the subspaces 3D to 2D to 1D, line to surface to what we call parallel, parallel of parallel point. This is what the matrix manipulation for subspaces it happens, and beyond that we get into beyond that it's difficult to conceive, and that's mathematicians are the best, and this is the what we call the instead of using matrix and of using the other proofs they have. And there was one thing that about the uncertainty. In the non-commuting exercise, I forgot to tell you about this. That when you measure in x-axis and z-axis two the spins simultaneously at the same time, that means then measurement cannot be 100%. There is uncertainty, and that is the uncertainty. I think I just looking why. So the word I was holding for was tensor. So beyond metrics, we have to get tensor price, which is what mathematics is. And I think that I have completed the portion which I wanted, and this will be part two of this, which relates to other things like operator rules, brackets, and maybe metrics and all that. Combination on projection of etc. and problems. So I thank you. I think with that I will stop the recording for. Thank you.